13, 14, 15, 16. Howdy everybody. If you've clicked on this video, then you've probably got a pretty good idea what this video is going to be about. I just want to say up front though that this is not the way I thought I would convey this concept, but after getting partway through the edit of like this enormous amount of footage testing aluminum versus wood, it had just become too enormous in scope and just not very easily digestible. So I've chosen to make this kind of like summary version that's basically going to summarize like the major themes of all the testing I've completed so far. That long version of this video though is also available to watch. That link should be popping up on the screen here somewhere. Gotta warn you though, it's pretty dense and pretty lengthy. In fact, there's a whole extra experiment in that video that I've completely omitted from this one because the results were just pretty boring. But that's like real experimentation. Even boring results are results, and that experiment did help me learn things. So if you're curious about that, please go and watch that video. Now, before we get to the testing, I just want to kind of set the stage and explain why I'm doing this testing and talk about some of the obvious limitations of them. Number one, the primary motivation to do this is me being primarily a woodworker. I keep coming across all these videos and all these forum posts touting how much lighter 80/20 aluminum extrusion systems are and how they have a superior strength to weight ratio. So I decided, why not actually test that and try to gain some understanding if that's true. Number two, if you consider cabinets you would build for a camper, an RV, or a conversion van, they're built a lot differently when they're made out of wood than they are when they're made out of these aluminum framing systems. And that's primarily because you're probably going to utilize some kind of plywood or some kind of sheet goods to build the cabinets. That said, with my budget and my time, I don't have the money to build entire cabinets and then attempt to destroy them. So the best thing that I could come up with was to essentially take wood and then dimension it into boards or members that allow me to build that same kind of outer framing structure, except building it out of wood instead of aluminum. I'm essentially building wood structures that have the same form, kind of the same dimensions as if you were going to build it out of aluminum. So that brings me to my third point. And that is that if you look at any of these aluminum framed cabinets, they can essentially be boiled down to two primary components, and that is long straight members and then 90-degree joints. So the test I did basically isolate these two components and test a wood version versus an aluminum version of them. Number four, if you look at my shop, it's pretty obvious that woodworking is what I primarily do, both as a hobby for fun and for income. It all kind of revolves around woodworking. So the joinery I'm going to be using later in this video to join two pieces of wood together, you might not be familiar with if you're just starting out. These joints that I'm using are very common for experienced woodworkers, but when I was a novice, if you had talked to me about bridle joints or mortise and tenons, I would have had no idea what you're talking about. But I say this because the purpose of today's video is to test aluminum versus wood and not the skill of the craftsman. So just please remember that these may not be very beginner-friendly methods, but they're just kind of necessary to see like what is wood really capable of when it comes to these tests. And that brings me to my fifth and last point up front here, and that I hope will kind of set the tone and kind of help you guys understand the lens that I kind of view these strength test videos through. A friend of mine, Eric, recently we were talking about something completely unrelated, but he gave me this great wisdom nugget that I think greatly applies to all these strength test videos and almost plagues them. And that is that I think people really fixate on and kind of inflate the importance of things that are easy to measure. When I look at all these strength test videos, almost, maybe even all the ones I've ever seen, someone sets up a rig where they slowly increase the pressure on some joint or some assembly until it just breaks. And that is great for an experiment you can like put a number to so you can compare two things together, but I think it's like completely detached from reality. Especially in the world of camper vans, I've never seen the failure mode to be like somebody stacking more and more weight on top of something until it breaks. What actually happens is, you've got a moderate weight like on a shelf, you're driving around every single day, it's constantly vibrating, it's getting bounced up and down every time you hit a pothole, or maybe worst of all, you're in like a catastrophic car crash and that causes things to just get destroyed. So this testing of like things slowly getting their pressure increased on them, it's great, it's entertaining, but I just don't think it applies to how things actually fail in reality. So the test I ran for this video, I tried to make them a little more applicable to real life and what I feel like are realistic scenarios or realistic things that matter, but I am well aware of the stupidity of all of this. What you're gonna watch today is like a silly simulation. I'm basically testing a piece of a cabinet, and that cabinet piece, the way it's built, is not even the way I actually build cabinets. This is all just a silly simulation but hopefully through this we'll gain a little bit of understanding, at least I feel like I did, of how these materials perform, kind of the pros and cons of both of them. So the two tests I'm going to present today are going to have to do with beam strength and then basically how the joints fail. I've made the assumption that the joints are much, much weaker than the straight members. That's how I've always seen things fail in life. It's always the joints that fail before the long straight members. You can argue with me if I'm wrong with that, but I've made that assumption for these tests. So we're basically going to test how much the beams deflect on their weight, and then we're going to fail the joints. But before we can do that, we got to really quickly talk about these materials and a few properties of them. Now there's going to be a few numbers that pop up on the screen as we talk about these materials. There's going to be a percentage at the top, then there's going to be like a cross-sectional dimensions, and at the bottom there's going to be some weights. That percentage is the percent of weight relative to 15, 15, 80, 20, which is the heaviest material we tested. And this percentage, along with the weights, is calculated based on linear weight and not like weight by volume. Essentially, if you were framing out a cabinet and you needed an extra little bit of this, how much does every extra little bit of it weigh? To me, this is a very functional metric versus volume, because if you are building a cabinet, you're using linear lengths of these things. Pay attention to the weight for the 10-foot section, as it really helps to easily convey how quickly these weights become very significant. So we have 4 different types of 80-20. 15-15 is the heaviest, and then there's 2 increasingly lighter variants called 15-15 light and 15-15 ultralight. All of these have that 1.5 by 1.5 inch outer diameter, but kind of the cross-sectional area, when you look at it, they're just a little more thinned out. And then there is the 10-10 80-20. This is the smaller cross-sectional area, but it is significantly lighter than any of the other 80-20 variants. Then we have an aluminum framing system I've used before called Moxitec. It's actually the lightest material in this test, and I've used it for a few projects. For certain applications where the project is really simple, it allows me to actually build faster and lighter than I found what I can do with wood, so I've chosen to use this for certain things. And then there's 2 wood species being tested. The first one is like American big box store framing lumber, commonly called pine, but if you're familiar with how things work in the lumber industry here, it could be spruce, pine, or fir. There's lots of things to be said about the quality of this material, but it gets used so much in vans that it seemed appropriate to test it out. And then maple is the other wood. If you are a wood geek, this is technically soft maple, and it has become my go-to wood for general projects. I like the aesthetic of it. The properties make it a pretty good all-around choice for most projects, and honestly, I'm just pretty familiar with it, so I'm comfortable working with it. Test number 1, the span test. The setup for this was very simple. I placed a couple sawhorses about 4 feet apart and then spanned the gap between them with each material. From the middle of the span, I hung a couple weights, specifically a 30-pound dumbbell and then a 68-pound battery, and then I measured the deflection using a little dial indicator. The results for this test were largely unsurprising, which often with these like DIY homemade tests is kind of the surprise. 1550 was the stiffest, deflecting the least, just over 200 at the 30-pound weight and just over 600 for the 68-pound weight. The 2 lighter 15-15 80-20 variants were progressively more flexible, and that 10-10, having the smallest cross-section, was far and away the most flexible of any of the materials tested. Moxitec, the other aluminum extrusion, and pine performed about the same, about twice as flexible as the 15-15 UL, and they both weigh about half of what it does. And most surprising to me, maple, even though it's about 50% heavier than pine, wasn't actually any stiffer in this test. But this test didn't quite end here, so let's take a little bit of a tangent as we consider that argument that aluminum has a better strength to weight ratio compared to wood. If you look at a very basic beam strength equation, you'll notice that the height of the beam is cubed, so any small increase in height has a proportionally huge impact on its stiffness. If you couple that understanding with how much lighter our wood samples are compared to our aluminum extrusions, I decided to test a couple taller beams that were still lighter than the 80-20 just to see how they would perform. The easy thing to test here was a full 2x4 from a big box store. Nominally, this is 1.5 inches wide and a whopping 3.5 inches tall. A full 2x4 like this still weighs about 25% less than the full 15-15 80-20 extrusion, and impressively, it's about twice as rigid, flexing only 50% as much. And then I tested a maple beam that was 50% taller than the 15-15 aluminum extrusions, so 2.25 inches tall. This thing is still 30% lighter, and it is about equally rigid as the stiffest 15-15 aluminum extrusion. So what does this all mean? Well, 80-20, if we consider that argument about strength to weight ratio, I think it's actually wood that's superior in this application. 80-20 is the best if you consider this a strength to volume ratio, but from a strength to weight ratio, wood is superior. So if you're building something where you can spare just a little bit of vertical space, even as little as like 3/4 of an inch, then I would just use wood. And if you're building maybe something like the bottom of a bed platform that no one's going to see, you don't really care about aesthetics, I would just use 2x4s. They're still lighter and way cheaper. So the second test I want to talk about today, I'm just going to call the drop test. And this one's going to take a little bit more of a preamble. So the first thing we got to talk about is how are those aluminum and all these wood pieces joined together so that we can test them. The 80-20 used a common single bolt on each side bracket they sell with the little plates and the little screws. One screw, one plate per side, holds it together, pretty self-explanatory. Moxitec uses these plastic corner connectors that are hammered into the extrusions, but are two different widths, had quite a few different joints I used, so let's quickly go over those. For the pine, I tested first pocket holes without glue, and then pocket holes with glue. Then we have half lap joints, which look like this before they're glued together. And then mortise and tenon joints, which look like this. For the maple, I didn't test pocket holes, but did test the half laps and the mortise and tenons and the third joint called the bridle joint, which looks like this. To do the actual experiments, I welded together the simplest little test rig, which is essentially I welded a little step onto this rectangular beam I had, and then I clamped that to a wall. This allowed me to secure our different little test pieces to it and then drop weights onto the protruding arms. If you're wondering why they were assembled into these U shapes instead of just basic L's, it's because for every 3 pieces of wood, I could get 2 joints to test. Instead of just making L shapes, it'd be 1 joint for every 2 pieces of wood. So that's why you're gonna see these U shapes throughout the rest of this video. The impact point that these weights were dropped onto was 12 inches from the supporting beam, and the progression of weights that was dropped was 2.5 pounds at a 2.5 foot drop, 2.5 pounds at a 5 foot drop, 5 pounds at a 5 foot drop, and finally 10 pounds at a 5 foot drop. If a joint survived 20 drops at a specific level, I would move it up to the next higher level, but there were times where those 20 drops at that lower level clearly had compromised the joint a bit. So for example, let's say it failed at the 5th drop of the higher level, I would run another sample starting at that higher level just to see if it could do better without that previous damage from the lower level. And here are the results. Let me just quickly explain how I've chosen to present these. Materials and joint type is on the left, and the drop level is across the top. The column the numbers are in is the level at which the test started. So for instance, looking at maple bridle, you'll see 20, 20, 14, which basically means it survived all 20 drops at the first level, all 20 drops at the second level, and then eventually failed on the 14th drop at the 3rd level. Then I took a new sample and just started clean, like an uncompromised sample starting at the 3rd level, and at that point it failed at the 15th drop there. And if you look at the samples, some of them have 2 different rows, and that just means I ran duplicate measurements just to see if there was some consistency. Of course, wood being a natural material, I expected there to be some variance, and that's pretty clear to see. So to highlight what happened, let's look at the results from the wood samples. Looking at pine first, no pine test subject made it past level 2. And in the maple, the bridle joint was the only one to make it to level 3. If we consider the actual joint types, pocket holes would cling on for a long time after the functional form was destroyed. And as to any difference for pocket holes with or without glue, if you held these joints together before we started testing, you would see that the glued joints do have some more rigidity. That glue does help it feel nice and tight. But in the actual testing, that glue plane being just essentially a butt joint failed very early, and then the joints performed basically the same, each subsequent drop just pulling that joint further and further apart. The half lap joint, which was tested in both pine and maple, kind of seemed like the joint most likely to just catastrophically fail. This joint relies entirely on that glue plane. There's no interlocking wood in the mechanism of it. So once that glue failed, it just exploded in half. So it was the most catastrophically failing joint, both species of wood. Mortise and tenon joints, having that innie and outer piece, kind of that interlocking mechanism, It did a better job basically holding on. Even when you could tell the glue was starting to get compromised, you actually had to break some actual wood fibers to get it to separate. And then the bridle joint with just that incredible amount of glue surface kind of sandwiching that middle member in there. This gets talked about more in the longer version of the video. This was far and away the stiffest joint of either material tested. And then in the actual drop test here, it did perform the best for any wood joint tested. 14. Oh, finally. Holy crap. Now, if you watch the long version of this video, you'll see a lot of the failures with the wood. If you look at these two kind of interlock, and when this broke, it snapped out. And a lot of this is what I call edge effect. There's just not a whole lot of wood between this mortise and then the edge of our test board. So I think I could have biased my results to help wood out more if I had just attached these kind of mid-member like this. I do a little bit of testing to kind of see how much stronger the joints are like this in the longer version of this video. But I would say to feel conclusive about those ideas or those observations I made, I would have to do more testing. So at this point, I just want to point that out, that edge effect really did plague a lot of these, and that is an advantage of the 80/20. It doesn't really struggle with that. So having said that, let's move on to the aluminum. Now, Moxitec did just about as well as our wood species, which was actually kind of a disappointment to me. I thought with the inherent flex of plastics, that the joints for this kind of framing structure, they would just kind of absorb that shock, spring back to shape, and essentially be more or less indestructible in this application, but that didn't prove to be true. Whoa! If you look at these corner connectors, they're actually not built symmetrically, and this end here appears to be weaker. I tested this both ways because the way the test pieces are clamped to the test beam, the arm sticking out is obviously going to get stressed more, and even in the advantageous position with the stronger side of the bracket taking most of the impact, the weaker end of the bracket still failed. So it would be interesting if Moxitec did make a symmetrical version of this bracket. They have some like quick disconnect function that I don't personally use. So even though the symmetrical bracket wouldn't have those features, to me, I think it would make a better, stronger bracket for these kinds of applications. And finally, 80/20. The 1010 extrusion, the smaller one, performed just about as all our wood species, worse than the maple bridle joint, but it was basically equivalent to all the other wood species. 16. The 1515 variants, however, were the only ones to make it to the level 4 drop test. So on paper, they are the strongest in this test. The 1515 and the 1515 Lite lasted well over 20 drops at the 4th level, to the point that the chain I was using actually failed before the joints were completely separated. In my notebook though, I'm going to say I summarized my observations with this as infinite but loose. So before I explain what I meant by that, I think the fundamental question this whole video has been kind of dancing around is, how do we define strength? Or maybe a better thing to say is, when you set out to design and build something, what properties of strength are you actually looking for? Every single material on this list has trade-offs. They have pros and cons depending on what you're looking for. Maple versus pine. I was so surprised that pine was just as stiff from a beam strength perspective as maple. I mean, when you pick up a piece or a board of both of these, the maple just feels so much more robust, so much more solid. And in some applications it is. The joints seem to generally be stronger. If you were going to build a tabletop, it doesn't dent nearly as easily. But if all you need is beam strength, pine is lighter, cheaper, and just as rigid. So coming back to why I wrote infinite but loose for the 15 series 80/20, well, even though it seemed like you could just drop weights on these brackets over and over, as low as at like drop level 2, these things started to develop some slop. I'd have to readjust the joint as it would rotate and slide and move around, and this is something I only had to do for the 80/20. The full 1515 did this the worst, because I think these little portions of the extrusion are solid versus sort of the toothed, hollowed out design of the lighter versions, which I actually think did a better job of sort of deforming and indenting to prevent the metal plate from sliding. This looseness would get so bad that for a couple samples, if I changed the direction the joint was loaded, like upwards, it would release the cantilever forces from the gravity keeping everything together, and it would just separate. We're in this boat now where, here, let me zoom you out a little bit. If I just, I mean, they're just totally loose, you know? There's so much nuance in how these materials perform. None of them were perfect, and I think that's really the take-home message here. At this point, I feel like the options are to continue to try to like split hairs, which is something you can do in the longer video, or we should just kind of zoom out and look at like what kind of the big themes are. In one sentence, I would summarize this entire experiment. 80-20 is stronger-ish if you ignore weight, as I don't think it has a superior strength to weight ratio. If all you care about is creating the most indestructible structure possible, I do think 80-20 is probably a good choice. But if you just consider the fact that you can dimension wood to a different size, and then like the realistic forces that these things are going to be subjected to, vibrations, twisting, bouncing, I actually think wood might be a better choice because it appears to stay tighter through those day in, day out events. So that's the take home message here. Some part of my brain now, like the curious part of it, wants to now build wooden joints that are dimensioned larger to see if they can withstand the same forces out of the 80-20. They would still be lighter, but they would, just be larger members because wood is less dense. But I feel like the practical part of my brain is kind of winning out right now. And the truth is that we got to remember, this was a silly simulation. I don't actually build cabinets like this. I just wanted to get a comparison of what wood was capable of versus 80-20, and whether all those claims that 80-20 is stronger and has a better strength to weight ratio. I think on the strength to weight ratio, I doubt it. And depending on how you define strength, 80-20 might be better. Anyways, I hope at least some of you guys learned something new here. When people ask me my thoughts on like building with aluminum extrusion systems versus building with wood, I give my honest answer, which is I think that a good builder and a good designer can build something great using either system. And I think the best builders I've seen know when to use one versus the other. Personally, I use 80-20 or aluminum framing pretty infrequently, mostly because I find it really cumbersome. It's really primitive in the designs it lets you actually execute. So for anything involving curves or something that you want to be really space efficient, I just don't think it's a very good choice. And I think 80-20 is really heavy compared to what I can build with wood. Anyways, thank you so much for watching. I truly do appreciate it. It helps me to push out one of these videos every few months as something interesting comes across that I'd like to share with you guys. So again, thank you so much for watching, and we'll see you next time.